Welcome to AI Paper Slop. Today we are looking at a July 14th, 2026 paper titled Long Horizon Terminal Bench, Testing the Limits of Agents on Long Horizon Terminal Tasks with Dense Reward-Based Grading.
Right. Published by researchers from Tencent, UMD, and a coalition of other universities.
Yeah, and we are skipping all the standard banter today because the core insights here are just too important. Here is the bottom line. Current frontier models still absolutely suck at long horizon tasks.
They really do. I mean, to prove it, these researchers built LHTB, which is this massive 46-task benchmark.
And the scale of these tasks is wild. The runs average, 9.8 million tokens?
Exactly, 9.8 million tokens and nearly 90 minutes of execution time. But the real kicker is that instead of the traditional binary pass or fail grading, they use dense partial credit rewards.
Right, which totally exposed the models. The absolute best model, Grok 4.5, achieved only a 28.3% success rate.
Yeah, it's a brutal reality check. What this paper proves that agents aren't failing because they lack local reasoning capabilities.
No, they are failing because they time out, they lose context, or they suffer from what the paper calls weak self-verification.
Right, meaning they just prematurely stop because they falsely believe they've finished the job.
Exactly. And this forces a massive shift in how we view the field right now.
It really does. I mean, the dominant narrative over the last year has been, that agents are practically ready to take over complex engineering workflows.
Right, just because they can ace those short, isolated tasks.
Exactly, in highly sanitized environments. But when an agent is actually forced to sit in a raw terminal for an hour and a half, managing its own memory, executing hundreds of sequential steps.
And debugging its own mistakes along the way.
Yeah, exactly. The illusion of competence just shatters almost completely.
It's crazy. And if you are an ML engineer listening to this and you're relying on older benchmarks, like, say, SW Bench or the early iterations of Terminal Bench,
Oh, well.
this paper suggests those evaluation methods were literally designed in a way that hid these specific failure modes.
They completely mask the problem. Let's unpack the core issue with those dominant benchmarks. They evaluate tasks within very short windows.
Like usually just a few minutes, right?
Right, a few minutes. And they rely heavily on outcome-only grading. So did the final state satisfy the test suite? Yes or no?
Which is just so limiting.
It creates incredibly sparse reward signals. Because in a long horizon workflow, an agent is navigating a file system, running shell scripts, inspecting partial outputs, iterating on bugs.
And a binary grade tells you almost nothing about the actual trajectory of that run.
Nothing at all. If the final test fails, you just get a 0.
It's like grading a dense 10-page mathematical proof by only looking at the final number at the very bottom of the page.
Oh, that's a perfect analogy.
Right. Imagine a student who works through 99 flawlessly reasoned steps. They are properly integrating complex functions, balancing equations, but then, they drop a minus sign on step 99.
Yep.
Under a binary grading system, they just get a 0. Their paper is completely indistinguishable from a student who just left the page blank or wrote down total gibberish.
Exactly. This binary approach completely obscures whether an agent made multi-stage progress or if it just, hallucinated a broken script in the first 30 seconds and gave up.
Right. It's totally blind to the nuance.
And if you map that missing minus sign directly to a terminal run, the equivalent is like a slightly malformed JSON output or maybe a missing environment variable at minute 85 of a 90-minute task.
And under SWE Bench, that's just a flat 0.
A flat 0. The model learns nothing from the evaluation, and you, as the developer trying to optimize your agent, learn nothing about the model's actual sustained capability.
You just see a failure in the logs and scratch your head?
Right. So if binary grading hides the minus sign on step 99, you need a grader that acts like a strict math teacher grading every single line of work.
Which meant the researchers had to just completely scrap the standard terminal setup and build something entirely new.
Right. Which brings us to the LHTB architecture. They engineered this subtask-based grading system, and they deploy it inside a highly controlled gauntlet.
Yeah, let's talk about that gauntlet. LHTB consists of 46 containerized tasks spread across 9 different categories, right?
Yeah, 9 categories. They cover software and reverse engineering, earth and climate science, scientific computing, multimodal analysis.
But they also threw in interactive games, which I found fascinating, like Super Mario, Chess, and 2048.
Yeah, that was a really creative addition. Each task is packaged as a harbor task, so it has a Docker image containing all the assets, data, and tools.
Right, and the agent is just given a natural language instruction and let loose in the terminal. But I want to pause on the gaming aspect for a second.
Sure.
Because, how exactly does an LLM agent attempt a game like Super Mario or 2048 inside a text-based terminal environment?
Well, it requires an entirely different operational paradigm than, playing with a joystick.
Obviously.
Yeah. In the LHTB setup, these games are headless environments wrapped in command line interfaces. So the agent isn't seeing a screen.
Right. It has no visual input.
Exactly. It's querying a state array, parsing ASCII representations or memory dumps, and then it's outputting specific, discrete commands like move left or rotate board.
That sounds incredibly taxing on the context window.
Oh, it is. To succeed, the agent basically has to maintain a massive state machine in its context window over hundreds of turns.
Wow.
It has to output a command, compile the next state, evaluate the reward shift, and decide on the next move.
So what does a 90-minute log actually look like for one of these gaming runs?
It is just a relentless, looping conversation between the agent's Python execution scripts and the terminal's standard output, just logging hundreds of tiny API calls and bash commands.
And grading that massive 90-minute log requires what the paper calls dense grading.
Right, the dense grading.
So the final reward, which they call R, is normalized between 0 and 1. And they calculate this using a mix of continuous, binary, and episode aggregating subtasks.
Exactly. So if the goal is to reproduce a specific scientific metric, the score might be a continuous value that just decreases linearly as the error grows.
Or if it's playing a campaign-style game, the score aggregates across episodes to measure reliable behavior over time. It's systematically tracking that partial credit.
Yeah.
But the detail I really want to focus on here, and this is a critical detail for you to consider when you are building your own evaluation suites, is the hidden stress suite.
Oh man, the hidden stress tests are brilliant.
Mm-hmm.
They completely neutralize the superficial hacking we often see on these leaderboards.
Right, because agents have a tendency to teach to the test, so to speak.
Oh, constantly. If they see a public check looking for a specific file name or a specific format, they will just hard code a bash script to print out exactly what the test expects.
Just totally bypassing the actual logic of the task.
Exactly. But LHTB prevents this by keeping the public checks very lightweight, maybe just validating basic CLI behavior.
But then behind the scenes.
Right. Behind the scenes, the final grader applies nested manifests, JITIP wrappers, injected noise, renamed data fields, and even missing values.
Okay, let's talk about the mechanics of how a model actually fails a hidden test, like a gzip wrapper. Does the agent blindly try to parse a compressed file as plain text and just crash the container?
That is exactly the failure mechanism. I mean, the prompt might ask the agent to parse a massive server log to find a specific anomaly.
Right.
So a naive agent writes a Python script using openserver_log.txt, reads it into memory, and searches for the error. And it works perfectly on the public test data.
Because the public data is just a normal text file.
Right. But in the hidden stress suite, that text file is secretly replaced with a zipped archive, or maybe it's injected with thousands of lines of corrupted Unicode characters.
Oh, that is sneaky. So what happens?
Well, when the naive agent script runs, it hits a fatal Unicode decode error, and the execution just halts.
But a robust agent would handle that differently.
Exactly. A robust agent anticipates this. It writes a generalized pipeline. It runs the Linux file command first to check the MIME type, dynamically imports the gzip library if needed.
Right, and wraps its parsing logic in try-except blocks to just silently drop corrupted lines.
You got it. It's about generalized robustness, not just passing a specific test case.
Okay, wait, I have a question about this. If the grading is continuous, does the model actually see that score ticking up?
What do you mean?
Because if the agent knows it just got a 0.5 for successfully unzipping the file, isn't it just using reinforcement learning mid-run to game the system and hunt for the remaining 0.5?
I see what you're saying. No, the dense reward is not a reinforcement learning signal fed to the model during the episode.
Okay, so it's blind.
Completely blind. The model operates entirely in the dark regarding its partial credit. It only sees standard output and standard error from the terminal commands it executes. The dense reward is calculated by a deterministic grader that runs inside the container after the agent calls the exit command, or after the 90-minute timer expires.
So it is purely an evaluation metric designed to give researchers a high-fidelity map of how far down the workflow the agent managed to get.
Exactly. So the agent is still operating under the illusion of a standard high-stakes terminal session where it just has to rely on its own intuition.
And they threw 17 state-of-the-art frontier models into this environment. Let's look at the leaderboard, because it is rough.
It really is.
If you hold these models to a strict 1.0 threshold, meaning a flawless run that passes every single hidden stress test, 10 out of the 17 models scored absolutely zero.
Zero.
And even if we relax the threshold to 0.95, which, forgives maybe a tiny parsing error on a hidden edge case, the mean pass rate across all models is a dismal 6.4%.
And the top tier isn't exactly acing it either. I mean,
Yeah.
Grok 4.5 is the undisputed leader, achieving a 28.3% success rate at that relaxed 0.95 threshold.
Right, 28.3% is the winner.
Yeah. And that is followed by GPT 5.6 Sol and GPT 5.5, which are basically tied at 15.2%.
Which is wild because we are talking about the absolute bleeding edge of commercial AI here.
Oh, yeah. Models that easily clear 90% on standard coding benchmarks.
And they are failing over 70 to 80% of the time when placed in a persistent environment.
It just shows how limited those older benchmarks really were.
Let's talk about the economics of these agents, because the token usage and compute costs here are staggering.
Oh, they are astronomical.
The average task on LHTB burns through 239 episodes, 9.8 million tokens, and takes about 88.9 minutes of wall clock time.
Right.
If you are footing the API bill for an agentic workflow, the Pareto frontier outlined in this paper tells a very compelling story about cost versus reward.
It really does.
Assuming public list prices as of mid-2026, Grok 4.5 is the value pick. It has the highest pass rate at 28.3%, and it achieves that for only about $11 per task.
Right. It anchors the optimal edge of that Pareto frontier. But then you have the budget pick, which is H3.
Yes, HY3.
It only costs about $3.62 per task. Now, its pass rate is low. It only resolved one task at the 0.95 threshold.
Right. Not great performance.
No, but it demonstrates that you can attempt these long horizon workflows without bankrupting your project.
True. But on the complete opposite end of the spectrum, we have the inefficient outlier, GPT 5.4.
Oh, man.
This model costs a massive $26 per task. It burns through 302 episodes on average. And what does it get for all that compute?
Barely anything.
A terrible resolution rate of 2.2%. It literally passed one task out of 46.
It's just earning money.
It totally shatters the idea that you can just throw a massive context window and endless tokens at a problem to guarantee long horizon success.
Yeah, sheer scale isn't the answer here.
But why is it spinning its wheels? Like, what is GPT 5.4 actually doing for 302 episodes to burn $26?
Basically, it gets trapped in infinite debugging loops. The model generates a script, runs it, and encounters a stack trace in the terminal.
Right, standard debugging.
Yeah, so it reads that stack trace, feeds it back into its context window, and hallucinated a fix. But the fix is flawed.
Like, maybe it breaks something else.
Exactly. Maybe it reverts a previous working component just to solve a new local error. So it runs the code again, gets a similar error, and repeats the cycle.
Over and over.
It does this 300 times until the harness forcibly kills the session.
Wow.
So local reasoning capability doesn't save you from global amnesia. It proves that time efficiency, how much functional progress a model can accumulate without looping, is a distinct capability.
Right. It doesn't just naturally scale with sheer model size.
Exactly.
But the dense reward system allows us to see exactly what is happening during those loops, right? Because we have continuous grading, we can see what they call the near-miss phenomenon.
Yeah, the near misses are crucial.
Across all 17 models, 62.8% of runs made partial progress, scoring between 0.05 and 0.95.
Right.
For example, Kimi K2.6 solved 0 tasks under a binary system. It looks completely useless, but under LHTB, it actually had 5 near misses.
Yeah, on that one task, grammar fuzz coverage hunt, it hit a score of 0.94.
That's incredibly close.
It is. It essentially built the entire fuzzer, achieved the code coverage, but it just failed to implement a final minor logging constraint that was hidden in the test suite.
And under old benchmarks, that vital signal of capability would be completely erased.
Yep. We would view it as a failure indistinguishable from a model that crashed on line 1.
So we know they are making progress, but what is the actual execution bottleneck that stops them from finishing? According to the data, 79% of all unresolved runs, and simply because the 90-minute budget expires.
Right, timeouts are the dominant failure mode.
The agent is still in the terminal, still typing commands, still trying to debug, and the harness just pulls the plug.
The models simply cannot navigate the search space fast enough, but the remaining 19% of failures are what the paper calls early exits, or weak self-verification.
Right, this is where it gets really interesting.
In these cases, the agent hasn't satisfied the hidden verifier, but it confidently decides it has done enough and calls the terminal exit command.
Let's dig into these false finishes, because I think this is the most mind-blowing part of the paper.
Oh, absolutely.
On the Apex Law 433 matter task, several models voluntarily stopped working when their score was sitting somewhere between 0.80 and 0.87.
Right.
And they did this with 20 minutes left on the clock. Wait, we keep focusing our training runs, our resources on making models better at single-step coding, right?
We do. We train them to write a perfect Python function from a detailed prompt.
But this data suggests the actual bottleneck for agents isn't logic, it's metacognition.
Yes.
This is exactly like a junior developer relying entirely on an AI autocomplete tool to write a feature. They see the local unit test turn green, and they immediately open the pull request.
Totally ignoring the integration tests.
Exactly. Completely ignoring the integration tests or the fact that they just hard-coded a database credential.
Yeah.
They don't lack the technical skill to fix the bug. They lack the judgment of knowing when a task is truly verified and complete.
That is spot on. The models are overestimating their completion state and drastically underinvesting in final verification.
They don't have that paranoia.
Exactly. They lack the architectural paranoia that a senior engineer develops over years of production outages.
Right.
A senior engineer knows that just because a script ran once without throwing an exception in standard output, well, that doesn't mean it handles the edge cases or scales to the full data set.
Exactly.
But these frontier models, they get a clean terminal prompt and immediately assume victory without writing their own adversarial tests to hunt for residual defects.
So the macro takeaway here for your own architecture is that to build better agents, you don't just need a model with a higher score on a coding benchmark.
No, you need models that can aggressively budget their time.
Right. Preserve state over hundreds of episodes without hallucinating past context.
And crucially, verify their own work with intense scrutiny before they dare to call exit.
Because a model's ability to generate code is now far outpacing its ability to critique and verify that same code within a complex, evolving environment.
Definitely. Until we solve the self-verification bottleneck, throwing more compute at long-horizon tasks will just result in, well, highly articulate, infinite loops.
So what does this mean for the future of your AI stack? I want to leave you with a final provocative thought that builds on these findings.
That's good here.
If frontier models fundamentally lack the self-verification required to judge their own completion in long-horizon workflows.
Meaning they are essentially overconfident junior devs.
Right. Will the future of AI engineering require a hard two-tier architecture?
Interesting.
Instead of trying to build one massive, expensive agent to do everything, perhaps you need ultra-cheap worker agents like H-3 generating the code, running the bash commands, and making the attempts.
Okay.
But they are strictly supervised by a separate, highly calibrated manager model.
Ah, I see.
And that manager's only job is to enforce time budgets, write adversarial integration tests to interrogate the worker's outputs, and basically prevent false finishes before presenting the final artifact to a human.
So a strict separation of powers. One model optimized for rapid generation and exploration, and another model exclusively optimized for verification, skepticism, and stopping judgment.
Exactly.
Given the massive cost inefficiencies we saw with models like GPT 5.4 burning $26 just to fail 98% of the time,
Right.
decoupling generation from verification might be the only economically viable path forward for enterprise workflows.
It is definitely something to mull over as you design your next agentic system. Thank you for joining this deep dive into the research. See you next time on AI Paper Slop.